Knowing what's happening around our stationary point will help us to identify what type we have. That is it a maximum, a minimum, or a point of inflection? And therefore that will help us when we come to sketch our graph. Let's have a look at the top graph there. We know that at the maximum turning point there, the gradient is 0. And what is happening before that? Well, the gradient is positive before it becomes 0, and then it becomes negative. So you can see there that we would be looking at a situation like this, where we have a positive gradient, a 0 gradient, then a negative gradient. At this one here, leading up to it, our gradient again is negative, it becomes 0, and then it becomes positive. We're looking at this scenario here. Negative gradient, 0 gradient, positive gradient. At point C, what's happening around that one? Well, again, it's positive, 0, and then positive again, because that's what happens with a point of inflection. We could easily have had a negative before the 0 and then negative again, but that would still be a point of inflection. So how does this help us in terms of sketching graphs? For this function, f of x equal to 3x cubed minus 4x plus 1, well, it's a cubic. We know we should have a maximum of 2 stationary points. And we are asked to state their nature and sketch the graph. Let's start off by finding those stationary points. And what do we know about stationary points? We know that dy dx is going to be equal to 0. So let's find dy dx. And dy dx is equal to 9x squared minus 4. And we're going to let that equal to 0. So you get 9x squared equals 4. X squared equals 4 on 9. So x equals 2 plus or minus 2 on 3. Well, that's our x values. It means now we have to substitute that in to get our y values. So let's do that. So having substituted in 2/3 and minus 2/3, we end up with the coordinates 2/3 minus 7/9 and minus 2/3 and 2 and 7/9. Okay, we now need to state the nature. So when we're looking at the nature, we're interested in the x value of the stationary point. So for the first one, it's when x is equal to 2/3. And we know that when x is equal to 2/3, the gradient is equal to 0, because that is our stationary point. Now we want to think a value just a little bit smaller than 2/3. So we could probably use x equal to 0 to make it easy for ourselves. And we want a value just a little bit bigger than 2/3, so let's use 1. Again, whole numbers will make it easier. Now if we substitute these values back into our gradient function, because remember we're looking at dy dx, when x is 0, dy dx would be equal to minus 4. And the value is not so important, we're just really looking at the actual sign. Is it negative or positive? When we substitute x equal to 1 back into dy dx, so we get 9 times 1 squared minus 4, and we actually end up with a positive 5, because 9 take away 4 is 5. So what happens there? We have a negative, a 0, and a positive, which means that we have a minimum turning point at x equal to 2/3. And then we go through and do the same process for negative 2/3. So negative 2/3, we know that the gradient is 0, and we take something a little bit smaller than it. Again, let's take something that is a whole number to make our life a little bit easier. Negative 1 is a little bit smaller, and something a little bit bigger in this case would be 0. Now we already know for 0 that dy dx is -4. When we substitute -1 in there, we get -1 squared, so we get 9 minus 4, we get 5. So looking at this one, what's happening to the gradient? It's a positive there, so it's positive, 0, negative, and therefore it is a maximum turning point. So we have a minimum turning point at 2/3 and -7/9, and we have a maximum turning point at -2/3 and 2 7/9. So we've found our stationary points. We know that one is a maximum, one is a minimum, and we've answered the first part of the question by finding them and stating their nature. The second part of the question wants us to sketch the graph. Now, sketching the graph goes back to what we've learnt when we were sketching cubics, and we need to have a y-intercept and our x-intercepts. So there was a lot of work finding those intercepts, not necessarily the y-intercept, but the x-intercepts. Because it was a cubic, we had to use long division, and then the quadratic came out to be something that couldn't be factorised easily, so we had to use the quadratic formula. So in the end, they are our 3 x-intercepts. Now, just to make it a little bit easier for ourselves in terms of graphing, I'm going to work them out as decimals, but when we label them on our graph, they'll be labelled as exact values. So I've identified all of the points on the graph, the x-intercepts, the y-intercepts, the stationary points. I know that this is a maximum stationary point. I know this is a minimum. Okay, so now what I want to do with a nice smooth curve is join all those points together. And obviously doing this with a pencil is going to be much easier and give us a better shape to our graph. Make sure every point you go through is labelled with its exact value. So for the function 2x cubed plus 1, we're going to do exactly the same thing again, find stationary points and state their nature. Now remember, it's a cubic, it has a maximum of 2 stationary points, but it doesn't have to have 2. And looking at this graph, most of you might recognise that it's in the x cubed form, where we usually have a point of inflection. So let's see what happens here. So finding the stationary points, we let the gradient or the derivative equal 0, so f dash x equal to 0. What is f dash x for this particular function? It is 6x squared, and we're going to let that equal 0. So 6x squared equals 0, which means x squared equals 0, x is equal to 0. So it really means that at this stage, there is only going to be one stationary point. So what sort of stationary point is it going to be? And what is the coordinate of that stationary point? When x is equal to 0, what does y equal? So when x is equal to 0, we're looking for f of 0, which is 2 times 0 cubed plus 1, so it is 1. So the stationary point is happening at the point 0, 1. Now we want to find the nature of that particular point. So how do we go about doing that? Well, remember, what we need to do is test around our x value to see what's happening with the gradient. So we know that when x is equal to 0, that f dash of x, or the gradient, is also equal to 0, because that's our stationary point. So what happens at -1? Substituting that into our gradient function, we get 6 times -1 squared, which is obviously -1 squared is a positive, so it becomes a positive because it's just positive 6. And this is what we're interested in, the fact that it's positive or negative. And a little bit after 0 would be 1, and again we're substituting that in, and that also equals 6, so we're ending up with a positive again. So what does that look like? It is a positive gradient, a zero gradient, and a positive gradient. Hopefully you're seeing there that we end up with a point of inflection, and we end up with a point of inflection at the point 0, 1. So we now have our stationary point, and we know it's a point of inflection. We do need to find our x-intercepts and our y-intercept. Y-intercept, let x equal to 0. Thankfully this time there wasn't as much work to find your y-intercepts and your x-intercepts. As per usual, y-intercept let x equal 0 and x-intercept let y equal to 0. Now let's set about plotting these on our graph. So we're really only dealing with 2 points here because our point of inflection and our y-intercept are one and the same thing. And we know what's happening around the point 0, 1. So we can just very lightly draw in, and then we're going to go through our x-intercept, which is about negative 0.79. And our aim again is to get a nice smooth graph that goes through our coordinates. So that is the graph of 2x cubed plus 1.